Hi, everybody. How you doing? Good. Let's take a look at resistors a little bit more. We started talking about resistors in series and resistors in parallel yesterday. Let's try one more example of that and see if we can make it pretty complicated and how we might simplify it. Again, if you are watching this live at home, feel free to chime in. We've got Hilda here manning the moderator station, and so if you have a question, just fire it off to her and she'll relay it to me. Okay, let's try this example right here. Okay, so we have a voltage V, and now we have a very complicated set of resistors. And let's label these R1, R2, R3, R4, and R5. And remember, the goal here is to get that entire circuit into something that looks like this. One voltage and one resistance are equivalent. And we need to find that R equivalent. What is the equivalent resistance of this circuit? And then once we do that, of course, we can determine the current in the circuit. Okay, how do we do that? What we said last time was start from the innermost point, okay, the most complicated innermost set of resistors. And it looks like that's going to be these two in parallel right here. So let's redraw the circuit as the following. R1, and then it splits. We have R2, and then those two in parallel we are going to replace with RP. And we'll call it RP3, 4, which means 3 and 4 are added in parallel. The other side of that wire went down to R5, and then the wires came back together and off they went back to the battery. All right, that's the first step. How do I identify that RP34? Well, we know that they add in parallel. So 1 over RP is going to be 1 over R3 plus 1 over R4. So yesterday we said at this point you could just plug in some numbers and then take the inverse of that to calculate RP34. That's perfectly acceptable. All right, so now we have a simpler circuit, and now we have to again go into the innards, and it looks like this 2 in series right here is going to be important. So let's redraw the circuit. Battery, R1, and then it splits, and we're going to have some RS in series on that side. We still have R5 over on the other side. Wires come back together and goes back to the battery. All right, so you're going to get a value for RP34 from this one. How do you get the value of RS over here? Well, those are just two added in series. That's not too bad. So it's R2 plus whatever we found in the first step, RP34. All right, now we're dealing with this circuit, and let's wrap around the board here, and we'll draw it over on this side. Okay, just like in the old game Asteroids, right? You go around one side of the screen, you immediately come back in on the other. Anybody remember that game? That was like the popular arcade game when I was a kid. We used to go down to 7-Eleven, put in our quarters into the Asteroids game, and there was always one guy that had like way more points than anybody else. He would sit there for like 3 hours playing the game, and everybody else stood there drinking their Slurpees going, wow, he's so cool. Okay, what were we talking about? All right, yeah, circuits, right? So let's take that circuit and bring it back over here, and let's simplify it again. So R1 is going to stay where it is. But now we have two that are, again, in parallel. So we need to draw a parallel resistor. and it's going to be parallel combining S and 5. Okay, and what is this RPS5? Well, again, we're adding them in parallel. So RPS5 is going to be 1 over RS plus 1 over R5. Okay, we found RS from this step, and so you can plug it in there. R5 would be given to you. You plug it in there. You take 1 over those, add them up, and then you take the inverse to calculate RPS5. And now we're at the last step. The last step is our basic circuit. 1 resistor, and now we can call that R equivalent. Okay, that's what they mean. When they say find the equivalent resistance, simplify it down to 1 circuit element, and that's your R equivalent. And now R equivalent is those two things added in series. So it's R1 plus RPS5. So there is a lot buried in that RPS5, of course. It has all the other resistors buried into it in some complicated fashion. But if you go through step by step and just calculate numbers, at this point you would just have a number for RPS5 and you can plug it right into there. And now if you're trying to find something like the equivalent current, well, we just go back to Ohm's law. I is V divided by this equivalent resistance. This would be the resistance of the circuit. This would be the current in that circuit. Okay? And like we said before, you can do this for extremely complicated arrangements of resistors. You can always reduce it to a simple circuit. Let's talk about how you might measure this stuff. Okay, you have done this in your lab. You've measured voltages. You've probably even measured current. And what you use is various meters. It's usually one meter that has a bunch of different settings on it. But let's say we go back to our basic circuit for a second. Battery and resistor. And I want to measure how much current flows. Okay? The way I measure current is I insert something called an ammeter. It's called an ammeter because it measures amps. Okay? The ammeter has to go in line with that wire. So I'm going to take a device and I'm going to stick it right there and I'm going to label it I for current. That thing is my ammeter. Okay? It has to be in line with the wire, meaning if you had a solid wire, you would have to break it, connect one end to the ammeter, connect the other end to the other side of the ammeter. It's got to measure how much current is actually going through it. Okay? If you have a circuit like this, and now you take your ammeter and you simply connect it with wires like that, this will measure 0 current. Okay, it's got to be in the circuit wire itself. You can't just attach it in parallel somewhere else. It has to be in series. Okay, an ideal ammeter, in fact, has 0 resistance because you don't want the ammeter to affect the circuit. If it did have resistance, then of course it would change how much current is going to flow through that circuit without the ammeter. Usually you want an idea of how much current is going to flow in that circuit normally, and if you put in another resistor right there, that's going to change how much current flows. If the ammeter has zero resistance, then it won't change how much current flows. Now, ideal ammeters, of course, don't really exist. So there's always some small amount of resistance that you're going to add to your circuit when you put the ammeter in. And so just by measuring it, you're going to change that current. And this is sort of an important consideration. Whenever you're doing physics, always remember, the act of measuring it is going to change the experiment a little bit. Okay? And there's basically no way around that. How do we measure voltage, right? If we were measuring current, we'd stick it in series, but now we want to measure voltage, which is something different, of course, than current. And now let's say we want to measure voltage. Okay? How do we measure voltage? Well, we use a voltmeter. Took them a long time to come up with that name. What should we call this meter that measures volts? How about a voltmeter? Where do you put the voltmeter? You put it across the resistor. Okay? You are interested in measuring voltage across this resistor. And so you have to take wires and connect it to either side of that resistor. If current I is flowing, then we know that there is a voltage drop across the resistor, and you can measure that with your voltmeter. Now, we want all that current to go through R. We want hardly any current to go through this arm over here, through the voltmeter. So an ideal voltmeter has a resistance equal to infinity. Okay, so it's the exact opposite of the ammeter. Ammeter has zero resistance. Voltmeter has infinite resistance because you don't want any current going through here. If you have an infinite amount of resistance there, no current can flow in that arm of the circuit. It won't change the measurement. Now, you guys have played with these things, and you, in fact, probably have a device that has an ammeter and a voltmeter, and can also, what do they call it? They call it an ohm meter because it measures resistance. Anybody know what that device is called, the ones that you guys have been using in lab? It's called a multimeter, because it's a meter that measures multiple things, right? It can measure current, it can measure volts, it can measure resistance. You just have to change the knobs on it, change the settings, and then change the connections on the front panel. Okay, so this is what you guys have been playing with in lab, multimeters. And typically whenever you go to Home Depot or someplace like that, you say, I need a voltmeter. They're going to sell you a multimeter. It's got everything built into it all in one. Okay, we've talked a lot about resistors in circuits. The next element that we need to include is capacitors. Okay, so what do capacitors do in circuits? Well, let's think about the battery again for a second. The battery has a positive side and a negative side. And the positive side is the long bar. The negative side is the short bar. Okay, so if you take a AA battery, the one that says plus, that's the long bar. Let's hook up a capacitor here in this circuit. Remember, a capacitor we draw with two equal length lines, which is supposed to distinguish it from a battery. And that capacitor has a capacitance C. If I put this capacitor in this circuit, it's going to charge up. Namely, there is going to be some positive charge on one side and some negative charge on the other side. Which side should have the positive charge? The top side or the bottom side? The top side. The top side should be positively charged. the bottom should be negatively charged. How do you know that? Well, the battery has a whole bunch of positive charge on that side of the battery. And it's going to push away other positive charge through this wire, and that positive charge is going to accumulate on the top of the capacitor. Likewise, the negative side of the battery, which has a whole bunch of negative charge on it, is going to push negative charge away and end up on the bottom side of the capacitor. Okay, so that original statement that we said, like charges repel, you can really discover a lot about circuits just remembering that. Like charges repel each other. So positive charge on this side of the battery is going to push positive charge away from it onto the top of that capacitor. How much charge? How much charge is on the capacitor? Well, I don't know. You guys know? We have a relationship between charge and voltage, right? What's the relationship? Q equals CV. I know C, I would give that to you. It's a number like 5 microfarads or 10 picofarads, okay? It's some set number that only depends on the geometry of the device, what it's made out of, and the geometry of it. And now if I attach a voltage to it, the voltage V is the same voltage across that capacitor, because everything else is connected by metal wires. So what's the charge on the capacitor? CV. Okay? This is the charge on one plate. Obviously the capacitor has equal and opposite charge on the other plate, so the net charge on the whole thing would be 0. But when we say what's the charge on the capacitor, we mean what's the charge on one side of it? What's that positive charge? It's Q. Okay, but let's try something a little more complicated now. Let's say we hook up 2 capacitors like this. We'll call this one C1, and we will call this one C2. Okay, so I've just added a second capacitor onto the first one, and it looks like we've done it in parallel as opposed to series. What is the charge on capacitor 1? Well, the voltage across it is still just V, because those are wires connected right to the battery. So the charge is going to be C1 times V. The charge on C2 is going to be C2 times V, because it also sees the same potential, right? It's also connected by metal wires to the battery, and so the charge on it is just C2 times V. So let's ask the question, what is the total charge that is stored on the positive plates of those capacitors? Well, we just add it up, right? Total Q is going to be Q1 plus Q2. Piece of cake. What is Q1? We said it's C1V. What is Q2? It is C2 times V. And now I have a common V in both of those, so I can factor it out. And the total charge is just C1 plus C2 times V. And that thing we can call C sub P V. This refers to parallel. We've added these things in the parallel configuration, and yet somehow their capacitance has added up, which is very different than resistors. Okay? When you add capacitors in parallel, you simply add their capacitances to calculate the equivalent capacitance of that circuit. Parallel capacitors add. Battery V. And that whole thing simplified to our simple circuit. one battery, one capacitor, but this capacitor is in parallel. And the rule for adding capacitors in parallel is you add up the capacitances. All right. By adding those two, we have in fact increased the capacitance. Okay? And one way to think about this is, it's just like you took these metal plates and you doubled their area. If these were equal capacitances, and I had two metal plates that were separated by that, and I brought them together, I would just double the area of the capacitor. And when you double the area of a capacitor, you double its capacitance. Okay, how much energy are we dealing with in this case? Well, remember, energy is CV squared. 1/2 CV squared is the energy storage in a capacitor. And so we have 1/2 CV squared in that one. We have 1/2 CV squared in the other one. And we know that we can add those up because we have some common factors. C1 plus C2, all times V squared. But C1 plus C2 is the exact same as CP. So this is 1/2 CP V squared. Okay, when you have a circuit like this and it charges up, the capacitor has energy in it of 1/2 CP V squared. The other type of capacitor circuit that we need to deal with is, of course, when we add them in series. So let's go back to our circuit, and now we're going to take capacitor C1 and we're going to add capacitor C2 in series. Okay, one after the other along the wire. Let's think about where all the charge is. On the top plate of C1, there is going to be positive Q. If there is positive Q on that top plate, then there must be minus Q on the bottom plate. Okay, the whole capacitor has to stay neutral. If there is minus Q on the bottom plate, then there has to be positive Q on the second plate of capacitor, on the top plate of capacitor 2, and therefore there is minus Q on the bottom plate of C2. There is a voltage drop across capacitor 1, which is V1. There is a voltage drop across capacitor 2, which is V2. Okay? But they all have the same amount of charge on them. So, Kirchhoff's laws told us the following. If we start at some point in a circuit and we go around the circuit, the sum of the voltage increases has to be equal to the sum of the voltage drops. And so Kirchhoff's law says the following. V going up minus V1 going down minus V2 going down has to be equal to 0. This is Kirchhoff's circuit law, okay, or his loop rule. If I move the V1 and the V2 over to the other side, then this just becomes V equals V1 plus V2. All right, but these things have the same charge on each capacitor, and there is a relationship between charge and voltage. The same charge on C1 and C2, and we know what that is, right? Q equals CV. So if Q equals CV, then we must have V equals Q over C. And therefore I can write V1 equals Q over C1, V2 equals Q over C2. And now I can take those two things and stick them right into this equation. And so what does this equation become? It becomes Q over C1 plus Q over C2. But we also know what V is in the case of the equivalent circuit. In the equivalent circuit, we have one capacitor. It was in series, and so it's going to have a value C sub S. And so I could say V is equal to Q over C sub S. And so this whole line right here equals Q over C sub S. And now you see exactly what happens, right? If I look at this equation right here, I have Q over C sub 1 plus Q over C sub 2 equals Q over C sub S. I can divide the right and left of that equation by Q, and I get 1 over C sub S equals 1 over C1 plus 1 over C2. And this is the rule for series capacitors. When you add capacitors in series, you add their inverses, whereas in parallel, we added their direct capacitances. Okay, so in this case, capacitance is in fact going to decrease. When I add two capacitors in series, the resultant capacitance is going to be less than both of them. The whole capacitance decreases. When I added them in parallel, the capacitance increased. All right, so let's see if we can summarize the rule for resistors and capacitors. So the resistors in series, we know how they behave. R sub S equals R1 plus R2. Piece of cake. But in parallel, we have to add their inverses. 1 over Rp equals 1 over R1 plus 1 over R2. Here we added resistances. Here we in fact added currents, and that led to the inverse of the resistor. For capacitors, we have exactly the opposite. So for series, we add the inverses. And for parallel, we add the direct values. Okay? And so you can see the symmetry here, right? Those two